In this section, section 2.6 on combinations of functions and composite functions, we are going to talk about domain from an equation, the algebra of functions, and composition. So when we find domain, we've talked about this before, that means we're looking for the set of x values for which our function is defined. It also means the largest set of real numbers for which the value of the function f of x has an output that is a real number. So when you're looking at it from an equation, you are, for now, looking for two conditions that could possibly cause a restriction within the domain. In other words, x values that cannot be used. The first condition is that we are not allowed to divide by 0, so the denominator of a fraction is not allowed to be 0. And the second issue is that any expression under an even root, particularly a square root, must be greater than or equal to 0. Because if it's not, meaning if it's negative, we would get an imaginary answer and not a real number. So if we have a fraction, we have to make sure the denominator value is not a 0, and if we have a square root, we have to make sure that the expression under the square root is not negative. So we're going to look at a few examples of those. So for part A, we're asked here to find the domain f of x equals 2 divided by x squared plus x minus 12. So since this function has a fraction, we have to make sure that the denominator, meaning the bottom, x squared plus x minus 12 is not 0. So we would set that up like this. Because it's related to 0, we can solve this one by one of our quadratic methods. So we're going to use factoring. So this one factors into the expression x plus 4 times x minus 3. So that means x plus 4 can't be 0, restricting x value of negative 4. And x minus 3 cannot be 0, so that restricts the x value of 3. So there are two numbers we have to exclude from our set. X can't be negative 4, so we have a hole in the number line at negative 4. And x can't be 3, so there's a hole in the number line at 3. In other words, all the numbers on the left of negative 4 are fine, all the numbers in between negative 4 and 3 are fine, and all the numbers to the right of 3 would be okay. So our domain, using interval notation, would mean from negative infinity up to negative 4, meaning this space on the x-axis, parentheses here because we're not including the negative 4, union with between negative 4 and 3, this interval, and then again union with the set from 3 to infinity on the other side. Our second example, we have some square root expressions. So this is when the second issue becomes something we have to worry about. G of x equals the square root of x minus 2 plus the square root of x plus 3. So the expression under the square root, x minus 2, must be greater than or equal to 0. And also the expression under the other square root, x plus 3, must be greater than or equal to 0. So solving the first inequality means you add 2 to both sides, so you get x greater than or equal to 2. And in the second inequality, x must be greater than or equal to negative 3 if you subtract the 3 from both sides. So if that has to be the case, on our number line, x values must be greater than or equal to 2, means from 2 and bigger, so this piece of my number line. X must be also greater than or equal to negative 3, which starts back here. So if both of those things have to be true, we have to look for where they overlap, or the intersection. So we would have to make sure that both are true, so we can't start here because the first one doesn't meet that requirement, so our overlapping space would be from 2 to infinity. So that would be our domain. We include the 2 because we're allowed to equal 0 under the square root as long as it's not in the denominator. Our last example here for domain has both issues. We have a square root expression and we have a denominator. So to take care of the issue with the square root, the x plus 3 would have to be greater than or equal to 0. And then also, because x minus 5 is on the bottom, that is not allowed to equal 0. Denominator can't be 0. Expression under the square root must be greater than or equal to 0. So solving this one gives me x greater than or equal to negative 3. And then solving this one gives me x cannot be 5. So I look at my number line. Here's negative 3. So if x was just greater than or equal to negative 3, I would shade to the right. But because 5 is part of that part of the number line, we have to put a hole here because we can't use 5. So that splits this up into two pieces. So a bracket at negative 3 up to 5 with a parenthesis is my first interval. Then I'm going to union sign because I got a second one to include as well. The parenthesis starting on the other side of 5, and then all the way to positive infinity. The next part of this section, we talk about what we call the algebra of functions. So just doing the algebra of addition, subtraction, multiplication, and division. So they ask us to find all 4 of those new functions and determine the domain for each one. So here we're given f of x equals 3 minus x squared and g of x equals x squared plus 2x minus 15. So to find the sum f plus g of x, we simply take f of x and add g of x. Because we're just adding, we can remove our parentheses and then combine our like terms in this case. So the negative x squared would cancel out with the positive x squared. Otherwise, I would have the 2x, and then the 3 minus 15 would combine to be minus 12. So 2x minus 12. The domain is simply the domain of f intersected with the domain of g. This doesn't have any restrictions because there's no fractions or square roots. Neither does this. So our domain is just going to be all real numbers. Negative infinity to positive infinity. F minus g of x, we take f, we subtract g. Here you do have to be careful because you're subtracting. This g of x especially needs to be in parentheses initially because we'll have to distribute the negative sign to remove the parentheses. So we don't really need them around the first expression, so we can just drop them since there's nothing in front. The negative will distribute, minus x squared, minus 2x, and then plus 15. Combining like terms gives me negative 2x squared minus the 2x plus 18. That's as much as I can do there. And then again, the domain is all real numbers. Fg, meaning multiplication, f times g of x. Let's take f of x and multiply it by g of x. So here we're just distributing. 3 times x squared is 3x squared. 3 times 2x is 6x. 3 times negative 15, negative 45. Negative x squared times x squared, negative x to the fourth. Negative x squared times positive 2x is minus 2x to the third. And then negative x squared times negative 15 is plus 15x squared. I'm going to rearrange to put them in highest power first and combine any like terms. So I have a negative x to the fourth term minus 2x to the third. I have a 3x squared here plus a 15x squared, so it's going to combine to be 18x squared. And then I have a plus 6x and a minus 45. Again, the domain is all real numbers. And then the quotient or division, f divided by g of x. There's f of x, 3 minus x squared, divided by g of x. Here we created a fraction because of the division operation, so since we now have a denominator, we will have a domain restriction. The denominator is not allowed to equal 0, so we're going to factor it into x plus 5 and x minus 3. So if this can't be 0, this one would mean x cannot be a negative 5, and this one set to 0 would tell me x cannot equal 3. So if I have to exclude negative 5 and 3 from my number line, we again would get 3 intervals. Negative infinity to negative 5, union, negative 5 to 3, union, 3 to infinity. Our last operation is called composition of functions, and it's indicated by this open circle. So this would be read as f composed with g of x. So that means that you are going to evaluate the first function, f, with g of x going inside of it. So we could write it as this, f of the function g of x. Similar to how we evaluated functions using function notation earlier in chapter 2. So let's say we're given f of x is 4x minus 3 and g of x is 5x squared minus 2, and we need to find f composed with g of x. So that would mean f of g of x, using this definition. So this would mean f, and then this is what g is, that was given. So that's what's going to go into the function f and replace the x. So we evaluate f using 5x squared minus 2 as a replacement for the x. So 4 times x, so I'm going to plug in this 5x squared minus 2 in place of that x, followed by the minus 3. I don't know why that didn't show up here. This should say 20. On my paper it did. So this would be 20x squared, and this would be minus 8. I don't know why that didn't show up here. Minus 3. And then this should say 20x squared. This was a minus 8 and a minus 3, so that should be minus 11. I must have had it written lightly or something because it did not scan. All right, so let's look at this next one here where all of it looks like it's written correctly. F of x equals the square root of x. G of x equals x plus 2. Here we're going to find f composed with g of x, g composed with f of x, f composed with g of 2, and g composed with f of 2. So part A, f composed with g of x means g of x is going to be evaluated in the f function. So we're going to keep f out here. Inside we're going to plug in g, which was the x plus 2. So then we take the function f right here and replace the x expression with the x plus 2, the whole function g. So that becomes the square root of x plus 2. Nothing more we can do with that. Part B, g composed with f of x. So this time f comes after the circle, so f goes into the g function. So g is first, stays here. F of x becomes the input. So since f of x was square root of x, that's what we're going to plug in for x in g. So g of x is x plus 2. So the square root of x is now our x. So that's our x. So square root of x plus the 2. Part C, f composed with g of 2. So this just means x is given to be a 2, and we're going to use that as the x value in the composition of f and g. So we already found f composed with g of x. That was part A. So we're just going to take that result, and we're going to let x be 2, plugging in a 2 for the x. So we get the square root of, plugging in 2 for x, 2 plus 2, both under the square root means add them together, so the square root of 4, which is 2. The other one, the other direction, g composed with f of 2. So again, this means x equals 2. We're plugging into the g composed with f function. G composed with f of x was this result. So in this function right here, we're going to let x equal 2. So the square root of 2, and then behind it is a plus 2. We can't combine these because one's a radical and one's not, so that's just our answer. And then our last example is working backwards. Here they give us a function, h of x, that is a composition, and we want to figure out what the f and the g were. So find f and g such that the function we're given, h of x, represents f composed with g of x. So in this order, this function that comes second, g of x, needs to be what's inside. F of x is what's outside. Inside is the 2x minus 5, so that's going to be our g. Outside of it, we're taking the absolute value of x, so that's going to be our f. So if I use this results for f and g and did